My name is John Skidgel, and I'm a UI designer, and I work on some of the developer products. And I'd like to welcome Brad Myers to Google today. He's going to be talking about the natural programming project, and I think a lot of his research is very applicable to some of the things that Google's trying to do around organizing information and providing APIs to users and making mashups and all those things much easier to do and create. So without further ado, let's get started.
Thanks. I think I have my own mic. Well, thanks very much for inviting me. I'm from Carnegie Mellon, and the Human-Computer Interaction Institute, in case you're not familiar with it, is a whole department focused on user interfaces that we have, about 20 faculty with backgrounds in computer science like me, but also psychology and design. So it's a very much interdisciplinary group. The presentation I'm going to give today is intended to be an augmentation of one I gave about 2 years ago here. So if you're not familiar with my old work, I'm sure you have the video somewhere. But I will be covering some of that in addition to all the new work we've done in the last 2 years. But I wanted to, particularly focus on the new work, because this is a fairly old project. The Natural Programming Project has been something we've been working on for about 12 years now. We started in '95 with one of my students. The fundamental goal is to try and make programming easier, to try and think about, suppose we were to take a human-centered approach to programming, and how can we think about making programming easier? And the general idea is to try and make it more natural. And by natural, I don't mean English. I don't mean natural languages like English or French. I mean natural in terms of the way people think. It's natural to just type in regular words into Google. It doesn't necessarily mean that you have to use natural language. And the methodology is also fairly unique, especially for programming research, in that we start off with studies. Okay, so we do studies of how people work. We do contextual inquiries into the field. We do a lot of background research in order to inform the actual systems that we build. And we always build some systems. We are a computer science group, after all. And then we actually go the next step and evaluate the systems we've created to try and get actual data about how well they perform. And that's also fairly unique in the software engineering field. If you look at software engineering research, it's mostly just claims about how good something's going to be without any data to substantiate it. But we really definitely try and get the data that talks about whether our results work or not. So if I'm talking to a bunch of people who are hardcore computer scientists or language theorists, they're very skeptical of this idea that programming should be more natural. If you talk to the programming language researchers, they want programming to be more mathematical. They don't want it to be more natural. So what is this idea of trying to make programming more natural? Well, we're basically coming at the perspective that programmers are by and large people, right? That even professional programmers are mostly people. And probably how many people here are programmers? So pretty much everybody. And you guys are all people. So why should we ignore properties of people when we're thinking about how programming is done? And there's been a lot of work in kind of the social aspects, how people collaborate around software, things like that. We're focused mostly on the individual programmer and the way they interact with their tools. And how can we deal with that in the same kind of, using the same kind of techniques that HCI uses when you're building a consumer product, like if you're building Gmail and you want to test it for usability, or you want to see what Gmail should do, you do certain HCI processes. We apply those same processes to the programming problem. So why is natural a good idea? If you think about programming, the whole point of writing a program is that you as the programmer have something in your head that you want the computer to do. And programming, one way to think of it, is a way of transforming what you have in your head into something the computer can understand. Right? So you have to take the task in your head. You want the computer to display this box or whatever. And you have to think about how you're going to get the computer to understand it, and you write code as a result. So our thought is that instead of trying to make the person do this transformation entirely, we can make the computer understand things that are closer to the way people are trying to think about their problems. If you think about direct manipulation, it's the same idea, trying to reduce the difference between what people want to express and how they express it. And then theorists like Green and Petrie have also identified this and with the parameter they call closeness of mapping, how close what you want to do is to the way you have to express it. And it's easy to see examples of this. If you want to sum up a set of numbers in a spreadsheet, you write sum, and then you give it the list of numbers. And in Java, you write a loop, and you have a loop variable, and you need 3 different kinds of parentheses and all these syntax and stuff like that. So clearly, a spreadsheet for the operation of summing numbers is a lot closer to your goal. Programming is not just for the professional programmers. Programming is pretty much for everybody. So there's a statistic that 30% of new jobs may require programming skills. This is US numbers. But of course, programming has always been complicated, and it certainly is still today. And another trend that we're seeing, and hopefully you guys aren't feeling this as much as programmers at other companies, is that there's intense pressure on programmers to be more productive. If they can't produce more code, they'll be offshored off to India or something where programmers are cheaper, and you can get more lines of code per dollar. So programmers are motivated now to be able to produce more code per dollar or whatever than they have been necessarily in the past. So there's professional programmers who have CS degrees. There's novice programmers that are people who want to be professional programmers, like students. And there's this new class of programmers that have been identified that we call end-user programmers. And these are people who program because they have to, not because they want to. Okay, they're programming as part of their job, and their job is really something else entirely. So they're not paid to program, they're paid to do something else, and programming is the way that they do that something else. So it's not a very satisfying definition, but it certainly gives you a sense of this big group of people we're talking about. And if you look at the charts and the numbers, it's really much bigger than this little group of professional programmers. These are US numbers. 3 million professional programmers in the US. If you ask people what they do at work, 13 million people say they do programming as part of their job. So that's already a factor of 4. If you include people who write spreadsheets, who write databases, who write web forms, then you've gotten up to 55 million people. And then if you look at all the people who use computers at work, that's 90 million people. I just ran across similar data from Adobe. This is worldwide numbers. They think they have Flash in their programming environments in about 2.4 million sites. But there's about 3.8 million what they call creative workers, designers and so forth who might use Flash. So that's kind of this group. But then there's like 80 million people who, are the potential markets. Okay, so you see these kinds of numbers pretty much in any field that you look at, that there's these very small number of professional programmers, but there's a much bigger group of people who are doing programming as part of their job, and we need to have tools for them as well. What about debugging? This has been a particular focus of my group for many years. It's expensive. Bugs cost companies a lot of money, and your average programmer, if you do a survey of what they spend their time on, they're spending about 3/4 of their time testing and debugging. Bugs are hard to fix by and large, and it takes a lot of negotiation among people and a lot of problem solving to figure out. And I think the really scandalous thing is to think about how you're debugging. We're writing print statements. We're setting breakpoints. We're watching variables. It turns out, if you look at the computers from the 1940s, they did that stuff too. What's new in debugging? Virtually nothing. That we're debugging today the same way we were debugging 60 years ago when computers were first invented. What other part of computer science has not changed in 60 years? right? Our programming language is the same, programming environments, everything else has really advanced significantly. Why aren't we spending more time on debugging given that it's such a big problem? So that's one of the things that really been focus of my group. And why is it relevant here? Well, there's kind of three classes of people that can benefit from this kind of research. There's internally, you guys have lots of programmers that work here. Suppose you could be twice as effective. Suppose you could produce code 8 times faster than you do now. Certainly some of the techniques that we're looking at have enormous potential for increasing your own productivity on your own tasks. And we've done lots of studies of programmers at Microsoft and at SAP and some other companies in order to try and validate and find out where people are really spending time, what the barriers are, and so forth. You're also producing what are called APIs, programming interfaces. You're producing things for other people to use, for professional programmers to use by and large. We have lots of data about how that should be done and about how you can make those programmers' lives easier and how you can really significantly affect what they're doing. One study we had showed that if you do something wrong, it takes twice as long to use an API as if you do it a different way. Okay, that's a really significant barrier you're putting up in front of people that are going to try and use your APIs. And then finally, you guys are getting into the end-user programming market with things like Google Gadgets and mashups and stuff like that. We have data that helps inform how you can create those kinds of environments so that people can use them more effectively. So as I mentioned, this is a fairly old project. John Payne pretty much started it, and he graduated 5 years ago now. Now he's working at Rand in Pittsburgh. He started off by studying how people naturally express computer algorithms. Okay, what are the standard things that a computer has to do? It has to execute a sequence of statements. It has to make a choice, conditionals. It has to iterate, have loops. There are variables. So we took all these, fundamental computer science principles and asked people to express them without telling them they had to do anything about programming, just to see what sort of things people would say. And from that, we gathered a lot of interesting information about how people think about programming concepts. So just for example, all the men and women in the room, raise your hands. Okay, so for the people who can't see, pretty much everybody raised their hands, except for some of the programmers who understood that because I asked for men and women, that's the intersection. And so only people who are both at the same time should have really raised their hands. And I won't tell who felt like they actually matched that criteria. So these are, people who are programmers have to learn that the word and in programming has nothing to do with the word and in natural language. It's just a completely separate concept that doesn't really have any correspondence between the two. Another thing that was very strong about the strong result is that people, when you're thinking about a set of objects and you're thinking about a single object, you think about them pretty much in the same way. Move a chair, move all the chairs, right? You don't have totally different constructs for dealing with groups that you deal with individuals, whereas in almost every spreadsheet, every programming language, every end-user programming language requires you to have totally different structures for dealing with iterations and loops than you have to deal with singletons. Okay, why is that? Well, historical reasons. And then another thing, so we talked about ands and ors, precedence doesn't make sense to people. Go to the store and buy something that's not an apple or a pear. So you come home with a pear, because everybody knows that not binds more tightly than or. So it's not apple or pear, right? So these kind of things that we take for granted in computers really don't make any sense unless you have a lot of training to understand what they mean. Another thing that was pretty obvious was event-based programming. People like to say when Pac-Man hits a wall, he stops, or when all the dots are gone. But some people like to talk in terms of constraints. Pac-Man is never allowed to walk through walls. Okay, so both of those made sense to people, and so you have to think about the implications of that. So we took all those results and built an interesting programming language designed for kids called Hands, and that's Handy the dog. And it basically embodies a lot of these results in a new language, which we then did a user study on and showed it was better than the alternatives. And so I don't have time to go into any more detail on this, but as I said, this is a long project, lots of results, lots of studies, and I wasn't really sure what to focus on. So if you're interested in any of these results, I'd be happy to come back to them or point you to some of the papers. So we've been mostly working for the last, I guess, 8 years or so on the programming environment, on debugging, on tools, on how you understand code, and not on the programming language itself as much. And I have 4 PhD students and a whole bunch of other students who've worked on this recently. And we've been focusing, again, on all 3 classes of programmers: novice programmers, expert programmers, and end-user programmers. So one of the things we did early was look at novice programmers as they're debugging and seeing what kind of errors they made. Okay, what are the bugs that people make in code? What are the implications of the bugs that they produce? And it turned out, maybe not very surprisingly if you think about it, that almost all the questions people asked about their code were why questions. Right? A bug happens, and then you're wondering, why did that happen? Right? It's usually pretty obvious what happened, and so now you want to know why. Right? An interesting result that really nobody had observed before was in almost 3/4 of the cases it was a why not question. Why did something not happen? I wrote some code, it didn't seem to work. I expected this to turn blue and it didn't happen. Okay, so that in this particular case, why not questions were vast majority. And if you think about the debugging techniques, breakpoints, print statements, they're particularly poor at why not questions, right? This code didn't get executed. Why not? Well, I put a breakpoint on it. Sure enough, it wasn't reached. Well, yeah, I knew that already. So then you have to somehow trace backwards and put a breakpoint somewhere else and see if that was reached. And so, the why not questions are particularly difficult. So what we did was, what people do is they make up hypotheses. I think I know why this is a problem. I will guess what's wrong, and then either try and do some debugging to figure out, to verify my hypothesis, or what novices tend to do, and of course experts never do this, they just go write some code to try and fix it, even though they're not sure that that's really the problem or not. Right? So it turned out that 90% of the time people were wrong in their hypotheses. And 2/3 of the bugs in the programs were as a result of people guessing wrong, not sufficiently verifying their hypotheses, and adding more bugs on top of the existing bugs as a result of guessing wrong. So that they would add some code in to try and fix something that wasn't broken, or they would fix it incorrectly. So we've got 2/3 of the bugs. 90% of the time people are wrong. This is one of the reasons debugging is so difficult. So we had the inspiration to say, suppose you could directly ask the question you have in mind. And so we actually implemented that. We implemented a system called the why line that has a button that says why. And you push on it, and it gives you a menu of questions, why questions, and why not questions. Well, how can you have a why not question? Obviously, there's an infinite number of things the program didn't do. It didn't go get me coffee, right? Well, it turns out you only have to ask why not questions about things that could have happened. And so it's pretty, if you think about it, there's a finite number of things the program could have done, because you can look at the branches that weren't executed, you can look at the event handlers that weren't fired, and so forth, and come up with a reasonable set of things that go in the why not menu. So the why line, like most of my systems, is a silly acronym. Workspace that helps you link instructions to numbers and events. You'll see many more silly acronyms to come. So the initial version of the why line was done in Alice, which is a programming environment by my colleague Randy Pausch. We picked Alice because we had control of the whole source. It was fairly easy to instrument. And the other nice thing about Alice excuse me, is that you can instrument that you can, was that me? You can create code really quickly because it's a syntax-directed editor. So that made it really easy to do experiments. So we could take an expert programmer and say, write this code in an hour, and they could actually produce something really effective because of the debugging. So this is the Alice environment, and we augmented it with the Y line and had incredibly dramatic results. People were 8 times faster using the Y line than the alternative. And their overall productivity went up by 40%. Okay, so these are fairly dramatic numbers. How many people have increased their productivity by 40% or a factor of 8 or something recently? And so we wanted to see, and the question is, okay, you did it for Alice, you know, that won't really work in the real world. Well, so what Andy did over the last summer, last year or so, has been re-implementing this for Java. So now we have a system that will do the Y line for the complete Java language, complete Java system, all the APIs, real Java code, you know, 30, 80,000 lines of code, Java programs. You can get this kind of interaction where you ask why questions about the execution. And, you know, systems programmers, you know, if you're working on your systems, you know, multiprocessing, you know, well, maybe you can't afford it for that, this kind of overhead that the system requires. But for everyday programming that most of the world does, and remember, we're not just talking about your operating system programmers or your system programmers. We're talking about the 80 million people who could be using these kinds of environments. Why not use the incredible power of today's computers to give you this kind of capability? So what does the Y line do? As you're executing your Java program, it keeps track of every single thing that happens. Every assignment, every method call, every process switch, okay, keeps that in a trace. And then separately, you can load up this trace and then debug and see what happened. And in particular, it has, as you're executing to collect this information, it slows down programs by about a factor of 5, which is comparable to most profiling tools. So if you've ever run, you know, memory checker or performance tools, they also do tracing. It generates a trace at about 2 megabytes per second. So, you know, that's, you know, not insignificant, but how much, you know, can you fit on your disk or in your memory? And then Andy's invented some fairly clever real-time algorithms for using this trace data to generate these why and why not questions. Now, you might imagine that a Java program does a lot of stuff. How could you possibly know what goes in your why menu, right? So if you wanted to ask a why question about what recently happened, you know, 300 million instructions recently happened. Which one do you want to ask about? It doesn't make any sense. So we have this neat interaction technique where you can point to something in the screen that you see that is wrong, and that focuses the questions just on that object. And remember, we talked before about hypotheses. Well, isn't this an hypothesis? You have to say what you think is wrong. Well, we've observed that programmers are very good at seeing what's actually wrong. People don't have to make a hypothesis about what they see that's an error. They just have to hypothesize why. So we let them show the system what's actually an error and use that as a way of focusing both the questions that are asked and the answers. And so then the pop-up menus just have a very small number of questions that are about the thing that you are pointing to. Because any particular thing only has certain numbers of things that can either happen or not happen. So let's see if I can get this video to run. Unfortunately, the video is a little bit too big for the small screen that they're making me use here. So.
One promising way to help people debug is to record a program's execution and then provide a user interface to explore the recording. This is the approach we take with the Y-line, a new kind of debugging tool. For example, here's a program with a problem with its sliders. The blue slider seems to have no effect on the color drawn. As we demonstrate this, our tool records these interactions. When we quit the program, the Y-line loads the recording. It then recreates a history of the program's output. This allows us to choose a particular point in time to ask about it.
So it's going back and forth.
Here I'm wondering why this color was black instead of blue. So I click on the stroke and ask why it has its current color. The Y-line then determines the cause of the color and shows a visualization explaining it. As we can see, the selected event is the use of the color that we asked about. The Y-line shows the source code corresponding to this event above, and the current state of the call stack and locals on the right. To find out where the color came from, we can click on this data dependency arrow. When we hover over the arrow, the same dependency is shown in the source code. When we click on it, the Y-line finds the origin of the value and jumps there in the visualization. This updates the source file on the call stack automatically. Here we can see that even though the blue slider was moved all the way up, the values used to generate the color that was drawn on screen were all 0, making it black instead of blue. When we look at the code above, we see that the blue slider was never used. There are 2 references to the green slider instead, so we found our bug. In addition to the features we've seen, the visualization also supports collapsing and uncollapsing groups of events. The Y-line also knows what code the user has source for, and de-emphasizes code that might be unfamiliar. This includes single events, but also unfamiliar calls that happen to invoke familiar code. We can also separate threads of execution to help detect unwanted interleaving.
Okay, so hopefully that was pretty clear, but we can talk about more later. So we did a user study of this, just a preliminary user study so far. We're certainly going to do a more elaborate study eventually. We took the Y-line and gave it to some novice programmers and compared that to professional programmers using Eclipse for exactly the same bug. And we get, about a factor of 2.5 speed up in time. As you might imagine, the Y-line takes you right to it in as little as 1 minute. Where to go? Yeah, from 1 minute up to 12 minutes, whereas professional programmers with Eclipse took 3 to 38 minutes. So it can be fairly tricky to find these kind of things without the right tools.
Can you do the other 2 measurements, professional programmers with Y-line and novice programmers with Eclipse?
Yeah, so we have a whole formal user study planned, and that's going to be Andy's final thing for his thesis. We haven't done it yet, but we're pretty optimistic that when we do the experienced programmers, novice programmers, the whole, we're definitely planning a complete set of studies. This is just, wanted to make sure we're in the right ballpark. You wanted to repeat the question? Yeah. Okay. So another system that I reported here before, so the Y-line for Alice I had reported before, but the Y-line for Java is brand new. We just submitted a Chi paper and an ICSI paper about it, so you're the first people to hear about it. This is, again, some old work. The idea is, why debugging of programs is good, but, Microsoft Word is doing weird stuff to me all the time. Why can't I debug that too? Right? So the picture just moved, or something changed to a weird font, and things like that. So we always want to ask why about these so-called intelligent applications. Why is this menu item grayed out? And so we added the same kind of capability where there's a why menu, or you can click on things and ask why about them, to a simulated version of Microsoft Word. And one of the key things was, sure enough, we showed that people could figure out why certain weird things happened very effectively this way. But also, we designed a toolkit to show that if you have an undo stack, which, of course, most applications, very few of yours do, but most other applications do. If you have an undo stack, to keep the extra information needed to answer the why questions was only about 20% extra code, okay? Because most of what's in the undo stack is how to do something, how to undo it. So all we needed to add really was the dependency information of what it actually affected, kind of the back pointers, right? So if I click on something that's bold, how do I find out what was the command that executed? So the toolkit implications of providing this very useful feature for users was fairly minimal. And part of the innovations in Crystal was it doesn't just give you why something happened, but it shows you the particular user interface option that causes it to happen, right? So we figure that people really don't want to know why something happens. They want to fix it, or they want to make it not happen anymore. So when you ask, why is the text changed from TEH to THE, it says, because this option caused this button to be, checked. And so actually what we found was experts, if they wanted to get to this checkbox, it's often faster to use Crystal, even if you know where it is, because it takes you right to the right option. I'm always forgetting where that is, right? And if you've used, Word 2007, this is even worse. Finding things. They totally reorganized it. Now you really don't know where they are. And also, Crystal puts down objects where things used to be. So if something moves away, it leaves down this invisible object so you can point to it and ask why things used to be there. We also studied novices trying to learn things. Nowadays, programming languages are a very tiny part of what you have to learn to do anything. Right? Think about Java, and then think about Swing and all the other libraries you need to use. C++ versus MSDN, right? Or the Google APIs. Basically the language itself is a very small part of what people need to know. And so what is it that people have trouble with? And we came up with a model that describes all the different barriers that people have learning to program, very few of which have anything to do with the programming language itself. Right? You've got to figure out all these different things you want to use, how you're going to pick which one to use, how you're going to combine them together, and then how to figure out what actually happened. We did another study of professional programmers that was really interesting, and we got a lot of mileage out of this study. We've actually used it in detail for 3 or 4 different papers. An interesting observation was for virtually any change to a modern program, you're going to have to touch code in lots of different places. We call it the working set. Okay? And it's fundamental to object-oriented programming and aspect-oriented programming that anything that you implement has to be distributed, right? You put some stuff in the initialization part and some stuff in the paint methods and then the event handlers. So if I want to add a new kind of button to my system, where do I have to put code to handle that button? Well, all over the place. And this is really fundamental to architectures, because if you reorganized your software the other way, well, then a different set of things might be co-located, but some other things that you want to do would then be distributed. So it's really no way around this problem. It's fundamental. How come today's programming environments provide you no help at all with this? So we spent a great deal of time annotating these very detailed logs of what people did, so we could really have a good understanding of where people were spending their time during these tasks. And you're probably pretty comfortable with these names. They had to read the code. This is code they were not familiar with. They had to edit it. They were navigating and so forth. But if you look at these in detail, one of the things that really jumps out is the amount of time that they were spent navigating is 35% of the time that they were trying to do an activity. And a lot of these navigations were, just using the scroll bars. Okay, they had all the Eclipse fancy jump to my source kind of things and search with text and things like that. But a substantial amount of the time was actually wasteful navigations that really were back to where they were, or things that they didn't know how to get to in an effective way. So again, we're getting a third of people's time wasted on something that could relatively easily be fixed. And so we tried to build a tool to help fix this. Michael Koblenz did a master's thesis on a tool called Jasper, Java aid with sets of pertinent elements for recall, that basically collects together lots of snippets of code and tries to present you those exactly the pieces of code that you need to do any particular task. The grand vision for Jasper is it would automatically collect these for you. We didn't ever get anywhere with that. So I'm waiting for a PhD student to do that work. But since he was just a master's student we just had the ability to hand collect these pieces. So it's an Eclipse plugin that lets you take little pieces of code. Also, you can take pieces of documentation that might be useful, and you can make textual notes that might be useful to remind you what you're doing or things that you've discovered and so forth. And you can collect all these together in a window and then save it with your project, check it in the CVS and so forth. And so the idea is that, if you're working on a particular set of code, you can get the initialization and the paint and all this kind of stuff all together in one place and deal with it together. So it was just a first step, but I think it is interesting kind of implications of doing this kind of study, figuring out what people are wasting time on and then trying to fix it. Another tool I reported here before, which again grew out of some of the observations from the same study, is that when people are trying to learn APIs, nowadays they don't go to MSDN and type something in anymore. They type whatever they were interested in into Google and see if they can find some relevant code as an example code. Right? So if you're using an API, chances are somebody has discussed it in a news group somewhere, and Google has indexed it. Somebody has posted some example code. There's probably lots of code out there. So there's also the vocabulary problem. If you don't know what it's called, it's really hard to look it up in the documentation. Whereas probably somewhere in the news groups or discussion groups or something, somebody has mentioned this word along with the right API call, in the discussion somewhere. So this is a lot more, using Google is a lot better than just searching code examples, because if you have the wrong word for something, it's not going to be in the code examples, but it's likely to be in the discussion and the bug requests and things like that. So what Mica does, Mica makes interfaces clear and accessible, is it uses the Google APIs, does a search. So here I'm searching for how to do full screen in Java, and if it turns out there is a get set full screen window command in Java, so that's handy. But there are all these other things that are also quite related. And so what it does is it takes your search, sends it off to Google, then looks at all the pages that result, pulls any Java keywords out and puts them over here and sorts them in a heuristic way to try and get out the most relevant ones. It also tags all of the research results that have code in them, code examples, and then it has a mechanism for pulling the code examples out. So it's just a cute little application that seems to help people find much more quickly what API call they want if they're trying to get something done. We also use the same data set to look at how people do text editing. Okay, so when you're using Eclipse, how do you edit compared to when you're writing a document in Word? Okay, so the editor, the commands are fairly similar. You can go forwards and backwards. You can click with the mouse. You can type spaces and tabs and characters, and you can delete words and stuff like that. So back in the old days with Emacs, we had all sorts of special commands for doing code, but mostly people don't use those anymore. And if you remember the Alice, it's a fully structured editor. You have to drag and drop everything. People don't like that. So is there something about the way people edit code that's different than the way people edit regular documents? And sure enough, there is. And so we take advantage of that in this toolkit called Barista. A barista is somebody who makes coffee, and this makes Java code. Stands for Basic Approaches for Rewriting Instructions as Structured Textual Abstractions. And the idea is that to try and find a middle ground between fully structured editors that nobody likes because it's too obnoxious, and plain not helping me at all kind of text editing that you get with Eclipse. So it obviously is going to have escape completion or IntelliSense, whatever you want to call it, where it pops up the completions of things. But it has a lot of other things too. There's no particular reason that you have to look at your code in the usual drawn out way, right? Because behind the scenes, it's all represented as XML anyway. So we might as well reformat it in a way that makes it easy to read. because everybody knows that 90% of the time you're reading code and not typing it. So why, make that more difficult than it has to be? People often want to look at alternatives. They're trying out different techniques, and they have to use comments and things like that to do that. Why doesn't the environment help you with, keeping track of sets of alternatives? So there's a whole bunch of different ideas, special commands you can provide and other kinds of visualizations that can make editing a lot easier and not penalize the expert that really, wants to use their mouse their keyboard really quickly and use arrow keys and type in backspace and so forth. So it's a pretty clever idea. I have some new work on APIs. So Google makes APIs that professional programmers use and you guys use internally. And it turns out that the design of an API is a user interface, right? So that you're providing to a set of people, which are the programmers, a way of getting at the functionality that you're trying to provide them. So suppose we treated the API itself as a user interface and did testing on it. And so that's what we've done. And we've done various studies of different aspects of APIs. You can take a particular API and do a conventional study on it. You give it to somebody and say, what's wrong with this? And they try and use it and give you feedback. But then you have to do one after another, and that's kind of boring. So we're trying to go up a level and say, are there some principles or patterns, software patterns, that we can talk about in general as a way of making it easier for everybody who wants to design APIs in the future? So we've done two detailed, elaborate studies, one of default constructors and one of factory patterns. And we look at things like learnability, what kind of errors people insert into their code as a result of the APIs, robustness, what they like, things like that. So first one was required constructors. So this is for all you object-oriented programming people. How many people understand this code? Most people in the room? OK. The idea is that normally when you have an object, the way to create it is you say new object, right? So if you want a foo, you say new foo, OK? And this one style says that you can create an object and it's empty. And then after you create it, then you can start filling it up with things. OK, so I have an empty object foo here, and then I'm going to start filling it with things, and then eventually I'm going to use it. OK, there's another thing where you say there's no way to create an empty object. You have to already have the values for it before you can create it. So it's called a required parameter or required constructor. And the conventional wisdom is that the required constructors are better because the API author is now telling the programmer, you're not allowed to have a foo without a bar in this case, right? A bar is fundamentally essential to having a foo, okay? And so having this required parameter, in theory, is telling the developer that. However, in our studies, we found the opposite. In fact, having this required parameter confused people no end. Everybody wanted to create an object first and then fill it up. One of the reasons was that it really interfered with people's learning of how to use the API. That they really wanted to figure out if they had the right object first. Is this object going to be the one I want? And then they fill it up. So we, as I mentioned, we studied both expert and novice programmers. He asked what kind of people we studied. It was both expert and novice programmers. And this is universal. It's across the board. And in fact, we looked at very specific APIs with which people were already familiar. And they still got this wrong. OK? So, and maybe it's a small effect. OK? In this particular case, you might imagine people could figure out ways around it, but it wasn't, people's first reaction, right? So if it also, it did not succeed in telling people that they always needed a bar, because people would just figure out ways around it. They'd pass in a null bar, right? So then at compile time, at least they'd get through the compiler if they passed a null here, and then eventually at runtime. It's not like as a foo implementer now, you can assume that you always have a valid bar because they could have passed in null. So you had to check anyway as a programmer. and get your runtime errors if they tried to use it without passing in a valid bar anyway. Or they destroyed it, and then, then when you use it, it's gone anyway. And the other point is that normally, if you're going to require the parameter, that means your programmer has to allocate a whole bunch of temporary variables, right? So it's my temp bar holds my bar as I create it up, and then I temp, this and that and the other thing. And then, so you have this long string of temporary variables whose only job is to hold this thing that you're only going to assign in something later, right? And so that's doesn't seem like that's more structured than saving it where you want it to go, which is in the object itself. So another one that's very controversial is this idea of factory patterns. This is a very strong result, and everybody hates this result. Every professional programmer I've given this lecture to says, no, wait, I love factories. So the idea of a factory is normally you want to create an object, like we said, you say new object. Well, with a factory pattern, you're not allowed to say a new object. You have to go to this other thing called the factory and get one, tell the factory to give you one. So instead of saying new foo, you say, give me a factory f, and f, give me a foo, or f.createWidget, okay? So the idea is that for some reason, you don't want the user to allocate objects with new. You have to go to this other place and get them. It's actually a fairly common pattern. It's used 61 times in Java, at least 13 times in .NET. The SAP software package, if anybody's ever programmed to that, uses these all over the place. Turns out that a lab study with, and these were all experts, nobody likes factory patterns as a user, okay? When you ask people to design an API from scratch, nobody's ever going to come up with a factory pattern. When you present them with real code that uses factory patterns, they're all confused. When you present them with a programming task that requires using a factory pattern, the current tools do not support that very well, and so they find it difficult. They add more bugs to their code, and it has a really dramatic impact on their performance. It took 2 to 5 times longer to write code using factory patterns than it does to write code that uses new. And you may be familiar that with a factory pattern is designed to provide certain abilities, certain features like avoiding allocating memory and reusing objects and things like that. And there are often other patterns that you could use to replace what the factory pattern does and still provide, the ability for people to create it in a way that's much more natural. So you have to think about whether you want to make this trade-off of making it more difficult for your programmers or not, right? And this is not a consideration that most API designers have ever made. Question?
Anything as far as the builder pattern or dependency injection?
So you asked about the builder pattern or
Dependency injection?
I guess I'm not familiar with those patterns specifically. But one of the things we'd be delighted to hear about is if you have patterns you think would be good candidates for studying, it would definitely be interesting to see what your insights are in terms of your thoughts about whether they're problematic or not.
So I'm wondering to what degree these particular results corroborate a hypothesis that many people have pursued, but as far as I know without collecting data, which is that the more concrete, the less higher order the expression, the more intuitive. So monads in Haskell, for example, allow you to you can explain them mathematically in a few lines of math. People who use it well can say amazing things in a few lines of code. It's very robust. But those whose brains don't take to that, that many order of remove from the actual data being manipulated can take years to learn it. Similarly, programming by example, the self-language, all these things are trying to take the programmer down the abstraction hierarchy to where they feel much more like they're programming with the concrete data.
So the question is, is this just a matter of concrete versus abstraction, or levels removed from the actual code. I think it's definitely plausible, but that's really not the only thing going on here, right? I mean, so in some sense, the factory patterns, is a little more abstract than just allocating things. But in terms of the previous result, neither of these really is more abstract than the other.
I would argue that the create set call is less abstract because you have the foo at the time that you're setting its bar foo.
Right.
You're operating on the instance as opposed to providing all of the things which will be used to create an instance that doesn't exist.
So you can certainly explain this as being more concrete, but I would posit that no one would have proposed that as a trade-off here if we hadn't done this experiment first. Okay, and so if you ask somebody without having presented this data first, which of these is more concrete, they probably would say, oh, they seem about the same on that dimension to me. So I think that, and some of the other things we have don't fall as neatly into that dichotomy, but certainly, taking these HCI principles of making things more direct, trying to make things match the user's mental model, certainly, encourage that kind of design thinking. And, one of the real principles of this line of research is to say we should be applying that to APIs as well. And that, but in a lot of cases, using these kind of high-level guidelines, both sides can be arguing for their design based on exactly the same principle. And so we see this in design meetings all the time. Oh, I want it this way because that'll be more concrete. No, if the other way will be more concrete. And it depends on what you think the user's mental model is. And we're providing a mechanism here that will let you actually do an experiment to answer that question, to provide a mechanism, a methodology, if you will, for how to do user tests on APIs to answer these questions and come up with something that has the potential of having a big impact on the way things are used. We've also done a lot of studies of reverse engineering, how people understand code they're unfamiliar with. How many people here have been on a project where they've had to pick up somebody else's code? Pretty much everybody. So it's a universal problem in real companies. People tend to stay at a company 4 or 5 years, and products last a lot longer than that. People are moved around amongst projects. And so it's a very difficult task. And the question is, why is it hard? What are the fundamental aspects of it that are hard? Is there something that tools can do to make it easier? Well, you can't really build a tool unless you know what the tool is supposed to do for you. And so certainly the Y line is going to be a really important tool for this, but we have other thoughts as well. And so we've done this very detailed study of a fairly complicated architectural task that we gave people to do in the lab and see how they tried to approach the problem. And we did both novice and expert programmers to see what the difference was. And we came up with a model of how people approach this task. And they are basically trying to discover a set of facts about the code. Okay, what is this doing? How is it working? These are the kind of questions they're asking. So they're seeking facts that will explain certain aspects of it. And they learn things. They critique facts. So if there's something wrong with this code, or I wouldn't be looking at it. Either I'm trying to add a new thing to it, or I'm trying to fix something. They're trying to explain things that happen, either things that they've learned or things that they think are wrong. What are the implications or what are the causes? They propose changes, and then they try and implement them. Okay, so we have a model of what steps people are doing. And then we have a model of what information needs they have at each level. Okay, so for each process, what do they need to know? What do they need to look at? What do they need to keep track of in order to achieve that task effectively? And not very surprisingly, experts do a better job at this. And they're also not surprisingly, is that they are able to come up with root causes, kind of abstractions of what's going on, compared to novices that basically just look at the symptoms. Okay, so they will recognize higher level patterns like, oh, all this code is trying to make a cache, or this is the update, mechanism that's causing this to happen, and things like that. So This kind of confirms prior work that has shown this kind of novice-expert difference. But we also came up with a fairly new model of what this information-seeking task looks like as a investigation of what we call update paths. So in modern code, there's all this stuff that happens, information flows from here to there. And a lot of what you're trying to find out when you're trying to understand code is how data moves around. When the user clicks on something, what is the path through the code that causes eventually something to happen on the screen? When some data changes on the network, what happens eventually to get it onto the screen? And you don't just want to know individual ones. You need to know, in order to do a change, all the possible update paths. Because if you change it down one path, you might break it down another path. So there's all sorts of really interesting implications about how you might investigate an update and these update paths. And it turns out that today's tools are really poor at helping you understand update paths. They're call graphs, but that tells you everything that could possibly be called, and they immediately get really branchy, and they're pretty useless. Whereas you want to know, after I click on this particular object, where are the implications in that particular case? And there are very specific questions that people want to ask. What implements this trigger? When I trigger this, what are the implications? Or tell me all the different triggers that cause this to happen, and so forth. And so we've come up with a set of about 10 questions that seem like they're going to be able to give you lots of great information about update paths. And we're optimistic that just like we did for the Y line, we can come up with a tool that will visualize the answers, have a menu of questions, and allow people to get the information they actually need much quicker. So I think, once again, we're seeing this result of doing a very deep and thoughtful study of what programmers really do, what they really need to know, as a way of guiding what the tools should do. I have another student working on something we're calling topes, but really it's natural data types. So if you ask an end user what type of data they work with, they're not going to say integers and booleans and strings. They're going to say, people names or dates or project codes or, social security numbers, things like that. So suppose we had a system where you could describe the properties of those kind of data. Okay, what does a person name look like? Well, the problem with this, and the reason programming languages don't have anything in them, is that almost all the rules are only sometimes true. A lot of them have exceptions, or they're usually true, or they're rarely true, things like that. And so we need to have the ability to say, things like area codes never end in 11. Turns out to be a rule that's true. On the other hand, last names usually start with a capital letter. So that's not always true, but it's usually true. And if you see a lot of lowercase letters, then you're less likely to believe it's that it's a name. And so using very specific rules like this, the system can give you more intelligent error messages. It can help validate things. And you can convert from one format to another. How many different date formats are there? Well, there's a finite number. Google's products do a fairly good job of letting you type in freehand and figuring out what you mean. But most other web-based applications require you to use all these pop-ups so they don't have to do this conversion. With this kind of tool, it can do the transformations for you if you just describe what the date looks like. And another important point is that office workers spend a lot of time taking data from one place and putting it in another. They take it off of spreadsheets and type it into web forms. They take it off the web and type it into spreadsheets. They take it off one web form and put it into another web form in a different format. And so there's a lot of this, transforming data. They take it off of paper or email messages and put it into forums. You can think of all the stuff secretaries have to do or clerks. And so the question is, can we help automate that using this kind of tool that can help you with the data and the data structures? And so another important point is that we've built this thing where there's a calculus for describing these and code to actually parse them that works in both the web and Excel, so that you can use the same types across both environments. And we built an interactive editor that we've shown end users can use to successfully describe patterns that are more accurate than you can describe with regular expressions and other kinds of, with random code, to describe how data is structured and how to parse it. The study we just finished that was sponsored by Adobe is kind of interesting. It's a little further afield from what you guys are probably interested in. We were looking at interaction designers, people who use Flash and Photoshop and, produce pretty user interfaces. They also producing, most of the websites and things like that. And we're looking at how they author interactive behaviors and what sort of results people have about why that's difficult and what people are doing with it. 31 results. That was really, the community took it very seriously. We got lots of really good feedback. And sure enough, people agreed that behaviors are a lot harder. 86% agreed that behaviors were harder than the appearance for prototyping. Probably these were programmers, didn't know how to draw. Not very surprisingly, virtually everybody uses sketches, to design stuff, when they're thinking about it. They use storyboards, and there are a bunch of other things, wireframes, site maps, things like that, flowcharts. But interestingly, everybody agreed that those are not sufficient. Okay? If they're trying to explain a behavior to somebody, they take their sketch and they write a lot of stuff on it. Or they take their pretty Photoshop painting and they add all these annotations to explain what all of this stuff does. Right? So the pictures by themselves do not describe the behavior. It's all these annotations that really have the information about what the behavior is. Another interesting thing is that if you think about programming environments and how we talked about programming when I started the talk, the concept is you have in your head what you want the computer to do. And the programming environment is all about letting you express what you already have in your head into the computer. That's not the way designers work. Designers have a problem and have no idea what the solution is until they start working. So they actually talk about designing by sketching. So they aren't drawing the thing they have in their head. They're creating the design as they sketch. And the same thing is true of behaviors. They want to explore the behavior. But today's tools do not let you do that. There's no way to explore 10 different versions of something. So here she's saying, maybe this one, I don't know. I'm just sketching and trying to explore some ideas. Maybe I'll cut this in half. Right? So she's actually, very quickly able to explore 2 different choices here. How would you do that with a behavior? You take 2 hours to implement one version and then 2 hours to implement another one. And how will you run them side by side? You can't even think about doing that. And most editors like Flash only let you have one window open at a time. Well, that's kind of dopey if you're trying to compare things. So nobody's really thought about how you might incorporate this idea of designing through the implementation, designing through the actual behavior creation as a way of guiding what the tool should do and how the tool should be organized. So that's one of the things that we're proposing to do in the future, is try and think about how you might do that. Another important point is that designers are generally producing their behaviors not as the final implementation, but rather as a prototype. So that means there's much less requirement that it be really solid and really software engineering kind of working really well. So maybe this kind of exploratory programming makes more sense in that situation than it would in for a professional programmer. So I thought there was some pretty interesting results. The other thing is that the obvious way to make programming a lot easier is to say, let's get rid of programming. We'll just give you a menu of the 12 different behaviors you need. And there are tools out there where you can drag and drop a set of predefined behaviors from a menu. Well, what we saw the designers saying is that won't do. They really need fairly sophisticated behaviors. They want to explore behaviors in the same way they want to explore what it looks like, right? So they're fundamentally about making things, innovative, interesting, beautiful. And they want to apply the same creativity to their behaviors as they do to the look. And if you think about tools like Microsoft Expression Blend, if anybody's looked at that, it fundamentally says, no, you're not allowed to do that. Expression Blend 2. 2 minutes?
Quarter after.
I'm supposed to stop. Okay. That you're not allowed to do that. You really fundamentally have to separate out the behaviors and give those to the programmers, and the design and give that to the designers. So I have this unrelated tool that I don't have time to talk about, which is really fun. It doesn't have anything to do with the natural programming project. It's just a search tool that searches by association. So the idea is that sometimes you remember words, and then it's really good to use Google stuff. And sometimes you remember where you put it, and then you can just browse to it. But what happens when you remember, oh, it's the guy that I met at this conference, and he gave me a card, and on the card I wrote this name, and now I want to go find the name, or something like that. So sometimes you remember things by what they go with. And so Feldspar is a tool that specifically helps you find things by what they go with instead of what they are. And so you basically, and I've got a really cute little video, you make these chains that eventually get down to something you remember. And by giving this set of constraints, it's built on top of the Google desktop. It lets you, trace down where the thing you're looking for is. So I have a 3-minute video of this, but I guess we don't have time to show that. And when we used it in the user study, not very surprisingly, when we asked people to find things by association, it's twice as fast. Well, that's what it was designed for, and sure enough, it works. And people didn't have any trouble using it. So to conclude, what is this whole natural programming project? Really, it's about taking HCI methods and using that as a way of guiding how to build programming environments. We do studies first. That tells us what to build. We build it, and then we evaluate the results. And the result is systems that really do work better. Thanks.